Okay, so what is the quantum mechanical version of Hamilton's equations? Well, we first use Ehrenfest's theorem, which says that I h bar d by dt of the expectation of an operator is equal to the expectation of the commutator with the Hamiltonian. Okay, note that if the operator commutes with the Hamiltonian, then the expectation of the operator remains constant in time. Okay, so this is applying Ehrenfest to the operators x and p. Okay, I might get lazy with the hats. Now, using this, and let's also use the definition of x. So first of all, let's look at p hat, right? What's the definition of p hat? Rather, what is this in terms of the x basis, the position basis? It's given by this. Okay, and x hat is given by ih bar d by dp. Okay, so now let's look at what the commutator is, the expectation of the commutator. So the expectation of the first one, right, is by definition, it's this commutator operator squeezed between the states psi. So let's write this in terms of d by dp. So this is going to be given by x hat times h bar. So that's going to be ih bar dh by dp minus, now h bar acting on x. So this is going to be h bar, h, the Hamiltonian, acting on ih d by dp. Okay, times psi. Okay. Now the second term is actually 0. And so we're left with the expectation, well, we can bring the ih bar out. So ih bar times the expectation of dh by dp. Okay, so this you can replace with ih bar dh by dp. Cancelling the ih bars, we get d by dt of the expectation of a position is equal to dh dp. Compare this with x dot is equal to dh by dp from Hamilton's equations. Now for the p dot one, Hamilton's equations in classical mechanics gives you this. And if you work this guy out right here, they're going to find doing the same exact thing. Oh, this should be expectation, obviously. You're going to find that this is minus ih bar times the expectation of dh by dx. So cancelling the ih bars, we get d by dt of the expectation of momentum is equal to minus this. Right, so it's exactly this, exact analog of the classical mechanical version.